My name is Molly Anderson, and as Executive Director of the Nantucket Atheneum, and on behalf of the Board of Trustees of the Atheneum, I'd like to welcome you to our second Geschke lecture of the season. But I just ask you first to turn off those pesky cell phones, please. For 179 years, the Atheneum has been bringing educational and cultural programs to our community. Although the Atheneum is a public library, 2/3 of our annual operating revenues have to be raised from private sources. So programs like we're about to enjoy tonight are only possible through the generous donations of people sitting in this audience and many others. The Geschke Lecture Series is made possible by grants from the Geschke Foundation and the National Endowment for the Humanities, and through individuals here tonight and in our community. I'd like us to take just a moment, because the Geschkes are here tonight, to thank them for making this possible. It's my honor to introduce tonight's speaker, Dr. John Donoghue. Dr. Donoghue received an AB in biology from Boston University and an MS in anatomy from the University of Vermont and a PhD in neuroscience from Brown University. Dr. Donoghue was the founding chairman of the Department of Neuroscience at Brown University and is currently the director of the Brown Institute for Brain Science. For more than 20 years, Dr. Donoghue has conducted research on brain-computer interfaces, and his laboratory is internationally recognized as a leader in this field. He's published over 80 scientific articles and has served on advisory panels for NIH, the National Science Foundation, and NASA. Most recently, Dr. Donoghue was asked to serve on the advisory committee for President Obama's initiative on brain research. For years, John has been coming to Nantucket with his wife, Karen, who's a pediatric neurologist, and their 2 sons, who are both now in medical school. They recently purchased a house on Nantucket where John and Karen enjoy gardening and grant writing amidst the peace and quiet of Nantucket. Please join me in welcoming Dr. John Donoghue.
Thank you very much to the Geschkes, to Amy and Molly, to the board of the Atheneum, to the whole library for this opportunity to speak. It's really exciting. I don't come here to write grants. As much as I spend a lot of time writing grants, it's really quite the kind of thing. I do a lot of reading and a lot of thinking about neuroscience here, but not spending huge amounts of time on grant writing. It is really wonderful because it's such a beautiful place to be here. We have a gorgeous view of the harbor and this beautiful room. And so what I want to do tonight is, I'm a neuroscientist. I love understanding how the brain works, trying to understand how the brain works. And I'm going to tell you about this idea of merging mind and machine to restore the brain. That's using technology to come up with creative new ideas to help people who have severe disabilities due to damage to their nervous system. But I want to weave this into a couple of different things. First, I want to tell you just a little bit about President Obama's initiative that I've been a little bit part of. And secondly, I want to teach you a little bit about neuroscience so that when you leave here today and you hear something, or tonight, when you hear something about how we're able to take the thoughts of someone and have them control a robotic arm, that you'll actually have some understanding of how that happens, that it's not magic, and that the science that all of us pay for from our tax revenues and all of the knowledge we keep in our libraries is worth having. It's a very important thing because it has been the base that has allowed us to have the knowledge to produce these really miraculous kinds of treatments. And I'm going to tell you about a bunch of them. So first, for those of you who don't know, the president on April 2nd announced what's called the Brain Initiative. I don't even remember, even though I'm part of it, the acronym stands for brain, blah, 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 neurotechnologies, but it's a what's called a grand challenge by the United States to try to better understand the brain. I was very fortunate in being part of a group of scientists who irritated the White House for about a year until they finally said, you know, the president's kind of interested in this and thinks it's a very important thing. And lo and behold, a few days before April 2nd, I got an email from the White House, which is always, I think, an exciting thing. And the email said, show up at the White House next week. So we showed up, we all funneled in, and the president came out and made this initiative that he's committing national resources and saying we have a grand challenge to try to understand the brain. We have many scientists, we have a large amount of federal funding going into understanding the, let me see if is that working okay? We have a lot of federal funding, but there are some gaps in our knowledge, and I'll try to point out where some of those gaps are. We have just begun this National Grand Challenge, and I'm part of a committee of 15 academics who are trying to guide the National Institutes of Health in how we can best invest to try to break down the scientific barriers to try to understand how the brain works. Okay, so why is the brain interesting? And I'd give you 3 points. I think there are many that you could use, but one is it is us. That is, the brain is the thing that sort of defines us as humans. Our brains are special. Each one of us has a very special structure to our brain that makes us special, and it defines us as a species. Another thing is that I think many people don't appreciate, but if we could make machines that work like our brains, it would really be transformational. I'll show you an example. And then finally, of course, is that brain disorders are devastating. That is, they rob us of many of the aspects of what we hold dearest as part of our humanity. So let's go through some of these things, and I'll talk about them. So it is us. What do I mean? So at least since the time of Plato, we've thought of the brain as an important structure. Interestingly, I was sort of doing a little background checking about what the Egyptians thought. And the Egyptians actually discarded brains when they mummified their kings. So they didn't think much of the brain. But by the time of the ancient Greeks. All right, so let me tell you a little bit about the brain. And just to give you an initiation, a lot of facts, of course, have to be left out. So we have about 100 billion neurons. They're tiny little cells that communicate with each other with chemicals that result in electrical impulses going around. We have something like 100 trillion connections. The brain is incredibly interconnected. And the interesting thing about those connections is they develop in us. Some of them actually regrow as we age and continue to regrow. But importantly, they're what's called plastic. That is, when you learn something, your brain really changes the connections between the brains. They don't grow new connections, they get stronger or weaker. And these changes, which is called neuroplasticity, accounts for our ability lifelong to learn. And it's actually an important aspect of preserving our brain function. It's sort of like exercising muscle, exercising your brain, keeps those synapses, the connections between neurons, very plastic. Now, in a simple view, the brain is really a processor. You take everything in from your senses. You have sense organs like your eyes and your ears, your sense of smell, your sense of touch, even the sense of where your body is in space, which we call proprioception. And that information comes in, and it results in typically either stuff getting stored in your head. You remember something, you see a beautiful sunset and you remember it, or you act on it. So there's action that comes out. And what neuroscientists do, of course, is that they look at all the stuff that goes on inside, and how do you take what you know in your head and what you're seeing and act upon it, come up with plans, come up with what I put up here called the mental stuff, thoughts, emotions, creativity, things that define us as humans. Now, we know, and we've known for a long time, that the brain is broken up into pieces where there's an area related to seeing. So if you have damage to the back of your head, you can go blind. For hearing, for movement, and even in the frontal lobe for planning. But in fact, it's much more complicated than that. And once the information comes in for your sense organs, it gets spread all over the brain. And so, in fact, a better picture of the brain is this tangle of wires. And one of the problems we have is understanding what this tangle all means. And we do know a lot, that it isn't just a complete crazy tangle, like a ball of yarn, but in fact it has structure. And we know some of these connections, but the connections are all alive. They're always changing, they're always interacting. And so this, if anybody doesn't know what this is actually internet traffic around the world. And the brain is like this, and it's always active, and we know something about, in fact, there is something from Melbourne, say, to Washington, there's a connection, but we don't know the kinds of information that traverse it, and more complicated than that is, what's going on in the brain is more like a peace conference where Moscow, Washington, and London are all on board having a conversation, and then a little bit later it switches to Paris and Moscow and Tel Aviv, and so the things are switching around all the time. And one of the big initiatives with the President's new Brain Grand Challenge is to try to come up with tools so that we can listen in on the conversations that are going on across the globe, or in the brain sense, across the whole brain. So these are big, big challenges, and we don't have the tools to understand them. They become important for disease, for example, because we think that many brain disorders like schizophrenia or autism are both wiring diagram problems, that is, the connections aren't right, but also they don't send the right kind of messages in the aggregate. So the third thing, that's sort of an interesting fact, is the brain really provides a filtered interpretation of the world, not reality. That was just the letters dropped off there. And what I mean is that we all think that when we look out at the world, what you're seeing is me here, but in fact it's your brain putting together all of the experiences of your life together with an interpretation of what you're seeing, and that's actually what's being created in your brain, and it's not reality. So let me give you a couple of examples of sort of these interesting things about the brain that show you that it's not truly reality. So which of these orange balls is bigger, left or right? How many people think the left one is bigger? How many think the right one is bigger? Ah, good. So I have some. So you know. So I have some friends in the audience here that know too much. But the fact is, they know because they've learned about this illusion. This is an illusion, and in fact, so I've even put a little circle on here. These orange circles are exactly the same size. And our brain, for some reason, it interprets the world. So reality is the orange circles are the same, but our brain can't see them that way. And even if you know this is an illusion, and you can tell me that I know for a fact they're the same size, you're doing it because you know the illusion, not because your brain is telling you that way. So perceptual system is getting into your cognitive system, the thoughts, and it's really getting confused, and that's one kind of confusion. Now here's another one. That's a kind of fun confusion. All right, so let's read off what these words say. So tell me, just say out loud, what's this word? Okay, now I want you to tell me the colors that they are. Okay, what color? Oh, doing very well. Yeah, you're doing well, actually. But was it harder to do that? Yes. So what's happening is, you're quite good at this, though. I'm really impressed. So what you're doing here is there's a conflict between the language system and the perceptual system for color. And the reason it's harder is because one of them overrides the other. The word one is kind of easy to say the words, but when the color's there and you have to name the color, that word thing is conflicting in your brain. But the point is, what you're seeing is exactly the same. There's no change in the world at all, right? So the third one, and now I'm going to change all of your brains except for hopefully that you haven't, none of you have seen this illusion, but so this is a nice picture. It's got some brown and white stuff. So what animal is there? How many? 5. So you're doing something now. So you're doing something now which is an amazing trick that there is no border here, but your brain is segmenting. And this is something that we have really no understanding of how you do this. But your brain is segmenting this picture, and it's looking at white on white, brown on brown, and it's actually able to put together images. Now, as you look at these, the horses now pop out. I guarantee you, if you ever see this picture again, 10 years from now, 20 years from now, those horses will pop out instantly. I have now transformed your brain in a way that's completely different than it ever was before. And so now, nothing has changed in the real world. This is the same image that you saw a few minutes ago, but it isn't the same to you, and it never will be again. And there's a whole bunch of these illusions. We really are interested in these kinds of segmentations because this is a very clever trick that the brain does, and we don't understand how it works. One of them is because we don't understand all these conversations going on in the brain. So if we understood some of these things, what if we could make brain-like machines? So here's some ideas of things that we really could do with brain-like machines. So the Google car, have everybody heard about the Google car? Trying to make a car that drives itself. So And what I like about this is that, first of all, it has to have this big thing on the roof, which is using GPS probably, so it has to communicate with a satellite. And it's got this big, probably 200-pound computer and processor in the back. And of course, all of us here know that a 16-year-old can get a driver's license and with a 3-pound brain can drive a car anywhere they want to in the United States. So, well, it's not clear who's more secure. So if we knew how to do scene segmentation, which is something you're doing all the time as you watch out for deer running across the road in Nantucket, you know, is it a deer or is it just brown bush in the distance? You do this very well. We're at sort of the edge of doing this, but not really doing it well. If we could do this, could we in fact have robotic assistants? This is the Asmo robot that can do a little bit, but certainly not as good as any human in terms of helping out. And we hope someday that these kinds of devices might be helpful in nursing homes, in hospitals, in various health situations where you might need to rescue someone in a dangerous situation for a human. And I did find this interesting one here. This is a swimming robot, and I think that the lifeguards at Surfside don't have to be worried. I think that this is a long way away. You can see this is not an elegant swimming motion, but even so, it's supported by these large props to hold this robot in place. So the point of this is that it would be great. We could do some very interesting things if we could emulate all the things our brains can do and control bodies like we do, but in fact, we're not quite there yet. So finally, I wanted to spend most of the time talking about brain disorders, and specifically talking about this emerging field called neurotechnology, and specifically using technology to restore lost function. So what is neurotechnology? It's basically using devices, physical devices that connect to the brain. Typically, they can be plugged directly into the brain, but they might be sort of on the surface or just a little outside. And they're being used we can treat nervous system disorders. We can use them to diagnose disorders of the nervous system. But what's really amazing is we're able to make what we call replacement parts to restore lost function. So this sounds like an amazing idea. You're going to use physical things to help blind people see, deaf people hear, paralyzed people move. And I'll show you where we are with that. So this is not completely novel, that putting machines inside our bodies. And this one, I challenge anybody. Do you know what that is? This is another technology that was very successful. Shockwave? Yes, it is. Excellent. It's one of the first cardiac pacemakers. And it's a classic design. So this gentleman has a cardiac arrhythmia. His heart doesn't beat in the right way. So they put a couple of wires through his chest into his heart, and they put a stimulator, that's this big box here, and a thing called an oscilloscope, which allows them to look at the waves of his heart. And they fiddled with the dials until they got it to beat properly, and it saved his life for a number of years. I think it was years. So this was sort of 1950s technology. It's classic. Keep in mind the sort of what I call the clunky cart of stuff that he had to push around, and the sort of wires through the skin, a very inelegant solution, but saved people's lives. Of course, everybody knows now that a cardiac pacemaker looks something like this. It can be put into your chest, and about 225,000 people a year get them, and it literally does save their life. And no one thinks about that. In the 1950s, if somebody said they're going to stick wires into your heart and shock your heart about once a second, you would say, gee, that sounds really scary. Now it's just a routine thing, and no one would hesitate to do it. So neurotechnology is sort of largely at the stage of these early pacemakers. But some of it's more advanced. So I'm going to tell you about some of the kinds of neurotechnology that's emerging. So one is, that really comes in two kinds. One is electrical stimulation. That is stimulating the brain, putting signals into the brain. One is to restore lost sensory function, so to get your senses back in when they're lost, like vision or hearing. And another one is for a kind of therapy called neuromodulation, and I'll explain what that is in a second. And the second way is to read out signals. That's the work that I do, and I'll talk about it more sort of in the second half. And that's to read out signals, and specifically to the major use of this is to restore movement, but also or to predict or detect abnormal activity in the brain. So I'll explain what all of those things are. But the point is, we put information into the brain or take it out of the brain with these kinds of devices. So one of probably the big success in this technology is what's called the cochlear implant. And the cochlear implant is used to help people who have lost their hearing hear again. So basically inside, sound comes in your ear, you have this little thing that looks like a snail, and in it there are about 44,000 little cells that have little hairs on the end of them. And as you hear me speaking, those hairs are wiggling, some wiggling more than others, and that's how you get different kinds of sounds in. And in most forms of deafness, those cells go away, they die. And so they're no longer able to deliver the sound to the brain, even though the fibers, the nerve fibers that carry that information are still there. And that's typically what happens in deafness. So what was done actually now about 30 years ago, and really beginning almost 200 years ago, the idea of could you put a little threaded electrode, the kind of sort of like a thick thread that has little electrode on them that can electrically stimulate the nerves that are inside this little snail cochlea and allow people to hear something. And in fact, in the early days, people were laughed at. This was ridiculous. That how could you imagine that 44,000 hair cells could be replaced with, now they have about 22 stimulating sites. And in fact, there are about 200,000 people who are hearing because of this technology. They can hear. And not only do they hear sound and detect sound, and initially that's what happens, and I'll let you hear a demonstration of that in a second, but they actually, because the brain is plastic, right? Remember, it can change, that as they practice with this, it gets better and better. So if this sound works, I hope, we should hear an impression of what this sounds like when the cochlear implant is first turned on. Oh, I did forget to mention, by the way, that this comes in, there's a little microphone that picks this up and delivers it into the cochlea. It's implanted by a surgeon. But so we listen to the, let's see if this works here. That little scratchy thing, that's what it sounds like when the cochlear implant is first turned on, and then later.
She's drinking from her own cup.
So it's a kind of tinny sound. People who have them say it sounds tinny, especially people who have heard before. It sounds tinny, but they're able to talk on the telephone. They're able to listen to music. It doesn't sound quite right. But as scientists are getting better and better at tuning this, actually the hearing gets better, and as the brain learns more and more, people can hear better. So this is really a big success. More than 200,000 people, including many children, I think as early as 6 months old, are getting cochlear implants now. Another big technology is the retinal implant. This is much earlier in development. The retinal implant, same idea, that many forms of blindness, the receptors in the eye that pick up light die in retinitis pigmentosa and macular degeneration, but the cells that carry impulses into the brain stay intact. So the idea is to get a camera, see a picture of the world, send it down to a little plate of electrodes inside the eye. It tickles those fibers, stimulates them, and you get an image. Now, it's not perfect. Here's a device that was just FDA approved from a company called Second Sight. Here's the device. There's glasses with a camera. There's a little transducer that transduces the information. Here's the actual thing that the surgeon implants into the eye. So each one of these little sites stimulates and produces something like a dot pattern like this. And so the image that they would see is something like this. So you can see, what is that? A hand. So even though there's not very much information there, you're using all of your mental processing capacity to know that that's a hand. And here's a video of one of the patients who's been implanted with this device. And you can see he's scanning. He's asked to point to the spoon. And it takes him a while to process, but you can see he's able to. So is this seeing? Yes, it's beyond simple seeing, but it's not elegant seeing. So there's a lot more to do. But we are at a stage where people can get these devices implanted. There are about, I think, 60 or 70 people worldwide that have had them so far. So it's not, not a big product yet. Another form of electrical stimulation is this one called neuromodulation. And the idea of neuromodulation is to take a circuit, one of those network interactions that are not going right, and to electrically shock it so you get it back into a rhythm that it normally needs. So there are rhythms going on in our brain, and some of these get imbalanced. One disease where that commonly happens is called Parkinson's disease, where you lose a chemical in the brain called dopamine. And when you do, there becomes this abnormal rhythm develops, and people will shake, they become very rigid, and they have a very hard time moving. And because of our fundamental knowledge of where the circuits are, surgeons are able, and this is a patient with Parkinson's disease. You can just see her walking, shuffly gait, very hard to walk, shaking. This device, which is basically like a spaghetti noodle that has stimulating electrodes on the end, is implanted by a neurosurgeon deep into the brain. That's why it's called a deep brain stimulator. And the deep brain stimulator gives electrical shocks to a tiny structure about the size of a Tic Tac candy. You have 2 of them deep in the brain, and that's a very important part of this whole circuit that's out of balance. And when you turn this on, it's really quite miraculous. This is the woman with it after. So there's really a huge and impressive effect. And I forgot to blank this out because I usually ask the audience, how many people do you think have had this surgery of having 2 noodle-sized electrodes stuck into their brain, which sounds like a pretty daunting thing to do, but it's now worldwide more than 100,000 people. It's really quite common. Now, again, we don't entirely know what's going on here, why it works so well. That is, it works better than we would have expected because the stimulation is really quite macro, quite big. And one of the other things we want to do with the President's initiative is to come up with better ways of stimulating. For example, for full disclosure, many people who initially have this stimulation become manic afterwards. They become quite hyperactive. And so we need ways of, and so is that because we're stimulating the wrong place, or is it stimulating too much? And those are very hard questions that we haven't figured out. But nevertheless, the quality of life is hugely changed. And it doesn't cure the disease, but it changes the person's life. So now what I've been involved in is the sort of sensing side. So for many years, I have spent in the laboratory trying to understand how we move. That is, how the brain commands movement. And I've worked in looking at the signals that come out of the brain and trying to interpret them and say, what is it when we say, I want to reach out and grab this microphone and grab it, what actually goes on? How can I do that? And I can grab the microphone this way or that way or any way I want to. And humans are particularly amazing in the number of skills that they can perform. They can do so many different things by transforming their plans into very complex actions. So we have been working on this device called the brain-computer interface, and also known by other names. And just to show you, and we call it BrainGate, is our particular brain-computer interface system. So what you're watching here is a young man, a 25-year-old guy, playing a video game. And his job is to hit these treasure chests and avoid the goblins. And he's doing an okay job. You'd say, if I had a 25-year-old kid that was playing this, it's okay, but not that great. But this is Matt Nagel. He was our first patient. He had a spinal cord injury high up in his spinal cord that prevented him from moving his hands at all. He has a small chip implanted in the movement part of his brain that picks up his thoughts about moving. We're running that out to a cart of electronics that's converting his thoughts about moving that cursor into the cursor motion, and he's playing the video game merely by thinking about it. So that's the first time he had moved anything since he was paralyzed. So I'm going to tell you, that sounds like magic, and that's the part I want to tell you, that I'm going to try to show you how this can actually work. And it's not magical, but it really requires the interaction of neuroscientists, of engineers, of clinicians to work together to make these kinds of products. So let me remind you that paralysis is not a disease, but it's a consequence of typically or very often disconnecting the brain from the body in various ways. So paralysis can be from spinal cord or various kinds of brain injury, from stroke, something called locked-in syndrome, which means that it's such a bad stroke that you can't move anything except your eyes, from cerebral palsy, which is another kind of damage to the brain, ALS, which is a degenerative disease, or known as Lou Gehrig's disease, or amyotrophic lateral sclerosis, and a bunch of others. But what happens in these disorders is that the signals that come from the brain about movement come down the spinal cord and they're interrupted. They can be interrupted by spinal cord injury or a stroke, or they can be cut off as they come from the spinal cord out to the muscles, and the wires can actually never get to the muscles, and ALS is an example of that, where they degenerate. Or you can even you can think of limb loss, limb amputation or injury, as in the Iraq and Afghanistan wars, where a limb is gone. And so now there's good commands coming out of the brain, but they have nothing to control. So there are about 5.6 million people that have some form of paralysis, so it's a fairly prevalent kind of condition. About 12,000 people a year have spinal cord injuries. About half of those lose both arm and leg control. And there's about 750,000 people with strokes every year. And of those people, about 130,000 a year are cognitively, mentally intact, but they can't move their arms. And so if you ever want to know how debilitating that is, go to work one morning and sit on your hands and see how debilitating that is. So the idea, so let me just, so one of the things I want to point out is how hard a problem motor control is. And I like this, my son gave me this video, so we all know how amazing athletes are and dancers. But this is a kid who is just a very adept, motorically skilled guy doing something, and pointing out all of the richness of things that we can do by integrating our senses with our movement. And so pointing out, copying this is a daunting procedure. In addition, and I've selectively chosen this, here's our Asmo robot friend. Watch, he's got to walk up a flight of stairs, just showing you how it's really not that easy a problem to solve. Now, as I said, I deliberately picked on that particular segment. But of course, even in our own lives, we spend a long time learning how to reach and grasp and do simple things with our arms, and it's a hard problem. So we don't understand exactly how this works. So the sort of daunting task we have is going from, taking brain signals out, going either out to the muscles or to the outside world when this connection is broken, is to create this artificial connection. How could we possibly do this? Well, we have a lot of challenges. One is, where would we even get these signals from? Is there a part of the brain where you can get these signals and pick them up? What kind of signals are they? What do they look like? What would we do? Do we know enough to take a signal? What is the sensor that could do that? Do we have something that could be in your brain for the rest of your life that could pick up these signals? How could you translate them? So you get these kind of crazy, confusing signals coming out of the brain. Could anybody make sense out of them? It's, if I was speaking in a foreign language, if you didn't have a translator here, you wouldn't understand any of it, even though I was maybe giving a completely coherent presentation. And then finally, what would you do with it if you could do this? So this is what researchers making neurotechnology for brain-computer interfaces are doing. This is what the technology was that Matt Nagel was using that I showed you a few minutes ago. So now I'm going to explain to you how we sort of went through the problem, showing you, I hope, how you can actually understand enough neuroscience to say, oh yeah, that kind of makes sense, and it really can be done, and why it should be pursued further. So in our brains, we have a motor area. That is, there is a place where your commands, as I'm waving my hand around here, there's a part of the brain that's particularly active. So it's called the motor cortex. It's a strip about 1 inch wide that starts on each side of your brain, from about the top of your head down to your cheekbone. And it's broken up into 3 parts. There's one for your leg, one for your arm, and one for your face. And that's why some people will have a stroke that will be up in the arm area, and their arm will be paralyzed, but their face will not be. It's really all about the geography of the brain. So we know where this is. We've known for about 150 years that people who have strokes in that area have arm deficits. People who get electrically stimulated there during surgery will have jumping arms, and so we know where that area is. So we have a target. We can say, okay, if we want to get signals about movement, we can go there. Secondly, we can say, okay, what is the signal we would try to get out of that region? So we want to try to extract motor commands out of the motor cortex. So you think of brain cells or neurons as little radio broadcast towers. I mean, really little. I would say thousands of them could fit inside a pea. So they're really tiny. And really, they are like little radio broadcast towers. When they talk to each other, they really talk by sort of touching each other with long connections. But they emit electrical impulses that we can use a fine needle to pick up. So these impulses are coming out of neurons, and they're digital. They're a pop. You'll get to hear some of them in a few seconds. But they're like a digital code. They're 0101. And again, if you don't understand that, I'll explain it a little better in a second. That's the code. Now, the problem is that the motor code doesn't come from just one cell. Probably during the course of this lecture, many of us are losing neurons at a rate of 1 every couple of minutes. So one cell is not all that important. So really the importance is in patterns of activity. So the information that's coming out is in a pattern of activity. So it's patterns of these impulses that are being thrown out. And in a way, you can kind of think of it like a QR code. Does everybody here know what a QR code is? Excuse me. So the QR code, if you think of it, imagine each one of these little black or white squares is like a brain cell, a neuron. And in fact, what's going on in your brain right now is those are flickering, black, white, black, white, black, white. And that's a code coming out. Now, you go to the store and you want to know what does that mean, you have to get out your little QR decoder, right? Take a picture of it and it'll tell you what it means. Well, that's what we need for the brain. So I'm not going to tell you exactly how all that is done, but let's just take one neuron, like one flickering thing, and then figure out what these impulses can possibly be telling us. So here's what we look at as neuroscientists. This is electrical activity coming from the brain with one of those little fine electrodes I talked about. So here's a cell emitting. And these things are the impulses coming out. So you can think of it as sort of a 1, 0. When there's an impulse, it's a 1. When there's no impulse, it's a 0. So that's what comes out of individual neurons. So in order to pick up a pattern of those, we actually had to invent a device that could pick up many of them, not just one. And this, over the past couple of decades, a number of neuroscientists have worked together to develop this 100-electrode array. It's actually only the size of a baby aspirin, so it's a really tiny thing. And it can be implanted by a neurosurgeon into the brain, and it can pick up about 100 cells all at once, so 100 of these things. So it's like a QR code with 100 black or white squares. Okay, so how does all this work? So now here's where you're going to become neurophysiologists. So this is the electrical activity coming out of your brain. There's nothing going on right here, so it'd be all zeros. And I were to say, so I'm recording from this one brain cell, and I would say in a person, now reach to the left. And we get one pop out of the cell. One electrical impulse comes out. And now I say reach to the right, and we listen to that one, and we get 5. Right? So we get 1 out every time we reach left, 5 out every time we try to reach right. So now we do what's called the decoding problem. And now I say, okay, we listen into the cell, and 2 things just happened. We got 1, and then and then later we got 5. So what happened when we got 1? Which way did you move? Left. When we got 5, which way did you move? Right. So you're decoding. So basically that's what we do. We listen into nerve cells. We take each one of those and we guess based on the pattern of activity that comes out whether you mean left or right. And we know from about 2 decades of work that this is pretty reliable. Now, it's not that reliable. One cell may be firing 5 erroneously once in a while, and another one might be firing 2 or 3, and we don't know how to interpret that. But by averaging across a lot of cells, we can actually get a pretty good guess. So we guess at what is going on. And in fact, one of the reasons why Matthew's little cursor on the screen was wobbly is because we're not guessing right all the time. But you'll see some more examples of that. So this is what decoding is. Get it? So cells are putting out impulses. We have a little device. We pick up the impulses. We listen in. When the impulses come out with an imagined or an actual movement, we build a map, and then we turn the map around and we say, okay, if you hear 5 spikes, that means go to the right. So this is the device that we developed for BrainGate. There's the array that I talked about. It's implanted by a surgeon in the motor cortex arm area. Everybody following me? You know all these things so far. It has at this time a plug on the head, so it goes, the wires come out through a plug. It goes through some signal processors, a cart of electronics. Think of the cardiac pacemaker, right? It's kind of clunky cart of electronics. Comes into a computer screen. And so when the person thinks, move a cursor, the signals are decoded and they become cursor motions. So we have a pilot trial, and when I say we here, it's actually my collaborator Lee Hochberg from Massachusetts General Hospital and me and our team has been working for since 2004. Matt was the first implant. He had a spinal cord injury. We've implanted 7 people so far, 2 with cervical spinal cord injury. That means they can't move their arms or legs, but can speak. 2 with brainstem stroke, which is a vascular or blood vessel burst higher up in their brainstem, so not only can't they move, they can't speak. And 3 people with ALS, whose spinal cord is degenerated and they don't have any connection to their muscles, so they can't move. And I'm going to talk mainly about 2 people, Matthew, patient S1 with spinal cord injury, and Kathy Hutchinson, who had a brainstem stroke 15, or actually at the time of the implant, 9 years before we put the implant in. So the video I showed you of spiking actually was from a human listening in their brain. So now I'm going to let you listen in on the brain while we have Kathy imagine moving, actually in this case opening and closing her hand or resting. And you're going to be able, and I think you'll be convinced to, when you listen in on the popping of the neuron, you'll be able to tell what she's doing just by the firing, the popping, the electrical activity of this neuron. And the reason I call it popping is because we play this electrical impulse through an audio monitor, and all neurophysiologists talk about the sound of neurons. Neurons have no sound, but you'll hear now that that through an audio monitor they make this popping. And there'll be a technician telling Kathy, in this case, to imagine opening and closing her hand. Hear it popping a lot. Slows down. Shuts off. So if we have the computer counting those things, we can tell, for example, something to move as a consequence of that one simple signal. Okay, so you've actually listened in on a human brain and listened into mental activity about imagining to move. So here I'm going to show you a video of Matthew early on when we first plugged him in and first started having him control a computer. And he's actually going to narrate because Matthew can speak. And he's going to show you opening an email, which really means he has to move a cursor over a little icon of an envelope. When he does, a message pops up. He'll read it and then move on. And then he'll draw a circle, and you'll get to see him draw the world's first neurally drawn, direct from the brain circle. So you can also see there's the plug on his head here. That's an envelope email message.
Congratulations, you were doing it great. Very good. Open the second email. Okay. It says, "Hi, we'll talk soon." Great. Now can you exit back to the Cybernetics desktop? Exit. You can exit. Excellent. So what's next? Next, I'm going to draw a circle. You're going to draw a circle. Wow.
So he'll try 3 times, and you'll see him get better. It's still a mystery why he gets better. This is not a good circle. This is an eraser. That's what wiped it up.
Okay. All right, try it again.
And if you can see yourself, just like he did, leaning to get the thing to go the right way.
Okay.
Not exactly a circle. So this was a little bit later. Yeah, a little bit.
Excellent. Now let's try
So he was able to draw a circle, and my favorite part is notice how, like a little kid with a crayon, he sort of closed off the circle. So not perfect. Why is it not perfect? Because we really don't understand the code that well. We understand it enough to do this, but not really well. So I think we have an adult enough audience that we can listen to profanity. So Matthew actually uses profanity often, this is his style. But we were so excited, we said, well, Matthew, you haven't moved anything physical in 2 years in this case, so we'll give you this mechanical hand. It's a motor-driven hand. And we said, okay, we're going to hook you up, and you're going to be able to move this hand, just open and close it, and tell us what you're thinking as you're opening and closing it. So listen very carefully to what he says as he, for the first time in a couple of years, does control something, really. I don't know if you heard that or not. So this really didn't do anything, but it was really a big step forward that we were saying you could actually control something physical. So what could you do with these kinds of signals? So one thing that we're working on is communication interfaces. If you're home and you can use a cursor on a screen, you can type. So we're working on a point-and-click typing interface. The other thing you could do is have a robotic assistant where you could have a control signal come out and go to a robotic arm, and if you wanted a drink of water, the robotic arm could serve you the drink of water, but it's under your brain's control. And here I've shown a device where it's all implanted in the body with a little miniature package, so this is a futuristic view. The same thing, you could use the same approach, and you could drive a prosthetic limb. And in fact, prosthetic limbs are being developed that are as good as our own arm. They're not quite there yet, but they're really quite good. And we would like to be able to control them directly from the brain, so an amputee could have this arm added, and you could control it. And lastly, and I think our big dream, would be to directly wire the signal back into the body here so that a stimulator going to the muscles could activate the muscles so a person could move their own arm again. And this kind of system, which is called an FES, or functional electrical stimulation system, is something that already exists. So if we can couple the brain signal to the FES system, people could actually move again. Okay, so this is all underway, but not done yet. But I will show you one example where, in fact, Kathy has driven a robot and controlled a robotic arm. So here it just shows you how sciencey it all looks. You know, this is not ready for home use. Here's Kathy in her chair. This is life support technology to help her get around, mobility, to see. She doesn't, remember, she can't speak and she can't move her body, only her head. And here she's connected up. Here's the electronics, and here's a robotic arm. And I'm going to show you just one thing that she did. She, again, at this point, it had been 14 years since she had served herself even a drink of water. She had, she's completely dependent on other people. So we decoded the signals related to reaching and grasping. We hooked it up to this robot arm, and we said, okay, Kathy, here's your morning coffee. You're going to drink your own morning coffee. So here she is. So this is the setting. Here's, this is the Providence VA Medical Center, Brown and MGH, the collaborators, the DLR, which is the German Space Agency fancy robotic arm. And Kathy is now controlling this robotic arm. And this is actually the second trial that she ever did of drinking her own morning coffee. So the coffee, she has to drink through a straw. You'll see she has a little trouble because she doesn't breathe that well. She does breathe on her own, but it's, she'll take a little time sucking up the coffee. So we had to say, Kathy, okay, that's enough, Put the bottle back down, so she has to put it back down. So once again, why isn't it perfect? Because we don't understand how the brain does all of the things that I can do, like by simply wiggling my fingers. We're getting there, but we don't know. And my favorite part is her expression afterwards when she looks up and then she has this big grin on her face where she's really excited about the whole thing. And there. So, yeah. So Kathy, actually, this was amazing. She became famous all over the world for being able to drink her morning coffee when the mind prevails. Why the Wall Street Journal decided this would be a front page picture, I don't know, but I think it's really wonderful and a great honor to our participants in our trial. But the story was reported very broadly. And you can actually see there's a whole 60-minute segments on her and on the trial. And then there's more videos online. You can see that video in greater detail if you want to look online. But as I was saying, to get this in the home setting, you can't have this where you have a technician in the room and plugs on the head and all this clunky kinds of stuff in the room. And we are working on miniaturizing all these technologies. And although, as I said, this is sort of the dream scenario, one of the things that's important to do is to get the whole plug off the head and get everything inside the head, which is a tremendous feat to take all those electronics, much more sophisticated than your cell phone, put it in a can the size of a matchbox, and we have done that. And then put it, and we just missed the video, but it'll come around again, or I'll start it again, where the implant goes into the brain, the little sensor. You can get a sense of the size. And then here's this can of electronics that goes on top of the skull, but under the skin, and will transmit the brain waves out. So that's being tested now, but it's not quite ready. It's a couple of years away from being applied to humans, where somebody like Kathy could use that system all day long. So the best metric of where we are is to compare us with science fiction, right? They're always the best sort of where are we? So here's Kathy today. So for those of you who are Star Trek fans, and you can correct me, but and I think the date is correct for Star Trek, but I don't know what the date really means. But let's say it's 1,000 years into the future. This is Captain Pike. He was injured. He can't speak. He can't move. And Captain Kirk is going to talk to him, and you'll hear I'll let it play out here. So this is really terrible decoding. It has to have 2 flashes, and then somebody has to interpret it. So we're already ahead of those guys, so we're 1,000 years ahead. On the other hand, this is Luke from Star Wars, and you remember he had his hand cut off, and in fact, he went into, I think, even a non-sterile room. A robot did the surgery, put a new hand on him, and within seconds, not only was he moving again, but he was able to feel. So we're not there yet. We're still, I don't know what year that took place, either far in the past or far in the future. So our vision of having a paralyzed person be able to move again, completely rewired with neurotechnology, is somewhere between Star Trek and Star Wars. So just to sort of conclude, I want to say where neurotechnology is very exciting. We're at a time where the President's initiative will help us drive these kinds of devices to help people with severe disabilities and hopefully people with less severe disabilities to lead a much more human, rewarding, rich life and be able to do things that they want to do in their everyday life, even as simple as just having your own morning, serving yourself your own morning coffee. So I told you about neuromodulation for Parkinson's disease, sort of tickling circuits back into place by stimulating them. This is being applied for psychiatric disease, including things like Alzheimer's disease. If you want to ask me about it, I'll be glad to talk about it later. To help with stroke recovery, for memory loss, all of those things are in early trials. For hearing and vision, we already talked about, and a whole range of other functions. And in total, there's about 300,000 people that have been helped with this kind of technology. I told you about using sensing to pick up signals to restore movement, but this is also being tried in a number of other disorders. For example, in epilepsy, to sense when something goes wrong in the brain, a seizure is about to happen, and try to intervene and stop a seizure from happening. These are also technologies that are developing. So there's really a lot going on. In addition, those popping noises, the spikes, the action potentials that you heard in the brain of a human, this is the first time we've ever been able to listen in to human brains at this level ever before. So we're now getting insights into how the human brain works that nobody's ever had. So with this new wave of understanding the brain, we're going to understand how the human brain works, I think, at a whole new level. And so you can find anything on the internet, of course. But so this is now, since I can't remember it, so this is President Obama's calling on the science community. I think it's calling on all of us to support education, to support science and research, because these are the kinds of things that can pay off for a grand challenge brain research through advancing innovative neurotechnologies. And we can see the buy-in. This is from some guy's blog. And I don't know how he did this, but it's sort of Obama with President Obama with a brain cap on. So with that, I want to tell you that all of this work was done, by many, many scientists, clinicians, and engineers, and it really takes a whole team, including my own work. I mentioned Lee Hochberg and also Professor Artur Namiko, my colleagues at Brown, and many other students that work with me that I thank for all of their help. And so I'll be glad to answer questions. Thanks very much. So, is it okay to answer a few questions? I have permission from the staff here. Yes. Who is, yes?
I noticed that you referenced the Christopher Reeve website, and I also noticed that the first implant was back 9 years ago in 1994. And I wondered whether Superman was ever a participant in any of these neurotechnology projects, or perhaps he was dead by that point in time, and if so, would they have been helpful to him?
Sure. Yeah. So there was 2006 was our early implant. He was still alive at that time. We did. Oh, the question was, could Christopher Reeve have benefited from this technology? And the answer is he could have. He did. We did talk to him about it. At that time, we really hadn't done. We were at the level of where you saw Matthew. We had done no robotic arm control. He was personally was much more interested in regaining control over his own body, and we're still not there yet. So, but he was quite interested in this. Interestingly, just to show you how important your senses are, Christopher Reeve died because he had apparently as best I know, had a small sore that got infected and led to a systemic infection because he couldn't feel it. You know, something as simple as that. So restoring sensation is also important. But the short answer is yes. Christopher Reeve is like Matthew, just exactly a person with what we call a cervical spinal cord injury who could have benefited at least to interact more, and certainly in over longer periods of time, we think control robotic arms and potentially his own arm. And there was another, yes, over here.
It would seem a natural place where this is going is that we would be able to connect fluidly with computers, memories of computers, CPUs, and as opposed to dealing with maladies. Don't we expand both our memories and our thought capabilities? Where are we on that path?
Yeah, so I guess I do have my phone. So you know, I connect with computers and I have a very nice interface, you know, my smartphone.
No,
So I know directly. So the first thing is that currently the only way we can get that rich of information out of the brain is to put electrodes up against the cells. Nobody here yet, I think, would like to have hundreds, thousands, millions of electrodes implanted into their brain to get a better interface, and it would have to be awfully good for you to want to do it. So you know, can we do a better job? Potentially, that's one of the neurotechnology initiatives as part of the President Obama's grand challenge, is can we get better technologies to interface with the brain? The other problem is there are so many signals coming out, and each brain is so uniquely designed and uniquely active that a rich interface like the one we already have is to me, is so far into the future that it's still a science fiction realm question, but it's very intriguing and it continues to come up. And I spoke at Google, and one of the guys came up afterwards who was a gamer. All of you know gamers, and he said, "What I want is a sixth finger, you know, so I can game with 6 fingers." So you know, these things will become more challenges. I think the ethical implications have already gotten discussion. There's already serious discussions, but will come on and on as we can look more and more into, you know, what's going on in your head and how is it working.
So what do you see as far in the future? Do you think like 50 years from now that will be fluid?
No, so I think that
Seamless or something?
so it depends on what you want to do. If you want to make a click on your screen, we could do that probably a short time. You want to do something completely so that the language in your brain, so what I'm trying to communicate is that is so rich and complex and works at a level that we don't understand, that we have to understand that first before we could even address that issue of making a fluid interface with the brain directly with the machine. But it is a very thought-provoking idea.
But in 50 years, where will you be?
So, do I have this? Hold on. Oh, I hope I have it, yes. Okay, so here's my answer to that question. So imagine you asked Alexander Graham Bell, and I found out that's an actor, not actually Alexander Graham Bell. You asked him, what's the best app for an iPhone, right? You know, he wouldn't have any idea what you were talking about. If you said, what is the, you know, so what's a flip phone going to look like? You wouldn't know what you were talking about. How about a dial phone? No idea. So if you asked him, when will the dial phone come out? We don't know. So I found out the first ideas of a telephone, Robert Hooke had ideas using electrical impulses in the 1600s. That actually was this idea. It was originally called the lover's telephone. I don't know if you know that. It was supposed to be a private communication channel. It's quite an interesting history. But I did put together this thing of, so here's sort of the history of the telephone. That took 130 years. And that's nothing compared to the brain, right? So at each of these phases, you can address a little bit into the future. But getting to be able to say when where are we? Here, maybe? You know, what are we going to look like in 50 years? I don't know. It's really hard to predict.
You were prepared for that.
No, I just got that. Okay. Yes, in the back, in the first. Yes, yeah, yes, please. Yeah.
Two questions. Cost of these various devices and approval processes. Are these things that become available to large numbers of people? You have to bring the cost down, and what kinds of regulatory approval are you facing?
So So the best devices are the cochlear implant and the deep brain stimulator, both of which are reimbursed, and they're both expensive. So there is a mechanism in place for the still relatively small numbers of people that will get these devices. And of course, as more and more of them are produced, sort of like the cell phone, they'll get cheaper and cheaper. So I think there's already a structure. Regulatory approval, stimulating devices, the deep brain stimulator for various kinds of applications has been, it's actually relatively straightforward to get approval because the FDA is more interested in the harm that you could do with electrical stimulation. We now know from 100,000 people that, it's not, the harm part is not so worrisome. So I think that the regulatory path is really moving forward. It's okay, but the FDA is a challenge. And yes, here.
I have two unrelated questions. One is you said you would talk about the potential applications for Alzheimer's.
Mm-hmm. Mm-hmm.
I'd like to know more about that. And the other is, I work in the space community, and you mentioned DLR, and I was very interested in hearing about the connection with this relative to space exploration. Now, we talk about robotics and humans going to Mars, that's what we're currently working on in the future. Can you relate this to sending, I don't know, robotically programmed beings to go there first as prototypes, or actually take humans there who are amplified with this technology?
Sure. So the short answer, sure. I think there'd be a longer answer, but that gets back to this other issue of interacting with humans. And Alzheimer's, how are we doing for time? Should finish? Couple more. Okay. So I just was gauging the length of the answer. So for Alzheimer's, I'll give you the quick answer, is that it was accidentally discovered that stimulation of a fiber path in the brain improved the cognitive outcomes of a person taking cognitive tests. They were being stimulated for a different reason. And so there is now a trial going on in the United States to electrically stimulate and try to delay the cognitive decline that occurs in Alzheimer's. So many of you may know that I think in the next couple of decades, about 50% of the people over 85 will have dementia. And the cost to society is unsustainable. And I was recently in China. In China, the estimate would be about 300 million people, which is pretty close to the population of the United States. So it can't be done. So anything you can do, so this is not curing the disease, it's like the DBS for Parkinson's, but if you could stave it off for 10 or 15 or 20 years, then other natural causes will take effect. And what's more important is the quality of life of the person. Unfortunately, those happen. but the quality of life would be maintained, not the devastating consequences of Alzheimer's. So stimulation is being tried as a way to slow the rate of the progression of the disease. Yes?
When plasticity of the brain came to our awareness, there were a lot of books and a lot of talk about keeping the brain young through games and crossword puzzles and whatever. And that seems to have shifted now to physical activity as being a more productive way to keep the brain.
So here's a plug for libraries. Reading. Reading. So I think that this is, probably, I'm speaking a little bit out of data. This is, without my personal knowledge of the data, but my speculation here is that the exercise is certainly good for the vasculature of the brain, to keep the nutrients going there. That's very important. But we know that as you use the connections in the brain called synapses, that they make and break, and you can keep them active by doing rich intellectual activities. That's why I think, I don't know if you know this, but the higher your degree of education, the longer you, or the less likely you are to have severe effects, or later in life it occurs. The dementia occurs later in life. So it's a real plug for reading. It keeps you intellectually active. So the answer is both, of course. That both activities are important. And maybe last question in the back there. Mm-hmm. So, the question is about stimulation from outside the head. And so we specifically are not working on it, but there are people at Brown and many other institutions working on it. I'll give you one example. So it is possible to influence the brain from the outside, especially in the stimulation part. And so there are a couple of ways of doing this. One of them is to use a magnetic coil, which will create an impulse. And when you put it over your head, if you put it over the arm area of motor cortex, and I stimulate, what will happen? Arm will jump. Good, you learned your neuroscience tonight. Your arm will jump. So it works. So you can prove that you can actually activate the brain. It has now been shown that with repeated stimulation over the frontal lobe for people with depression, you can decrease the symptoms of depression. In some people, it's quite dramatic. So this is now already an FDA-approved therapy, and there's a manufactured device that's at clinical settings that you can get stimulation, magnetic, and it just feels, it feels actually, if you just tap your finger on your skull, it's what it feels like. And it magnetically stimulates the front, or actually electrically eventually stimulates the frontal lobe and helps ameliorate the symptoms of depression. So these kinds of things are being tried for all other kinds of disorders. Okay, so thank you very much. I'm really grateful for being here.